Welcome to the Crazy Hat Chemist, so another video in intermolecular forces. Bam! So today we're talking about intermolecular forces in a dipole-dipole interaction. Those are two permanent dipoles. So when two polar molecules, molecules with permanent dipoles, interact, the positive end of one is attracted to the negative end of the other, just like a bar magnet. Hopefully you've played with one of those bar magnets or two of them when you were a kid. Okay? This causes the molecules to align in an ordered arrangement like magnets, even in the absence of an electric field. Okay, so here's an example. I got a dipole-dipole interaction. This is a molecule with a charge separation. Because it's polar, it has a charge separation. There's a delta positive and a delta negative, and there is a dipole moment. Notice the tip of the arrow is pointing towards the delta negative, and the positive end of that arrow is a delta positive. I always imagine that if I were to take a bow and arrow and shoot it, then it would stick in you, and you would be like having that the negative end of that tip of that arrow hurting you, and that's why that's negative for you. But I would get to see the feathers, and that's positive because I know that I've hit my target. So this molecule with a permanent dipole has a dipole moment, i.e. it's a polar molecule. Okay, there's a second molecule, and it is going to interact with the first previous molecule. This is a dipole-dipole interaction. Notice that the delta negative at one end is aligning with the delta positive at the other end of the other molecule. And it's an intermolecular force that's between two different molecules. Okay, we can add another molecule in here as well, and this is also a dipole-dipole interaction. Okay, and then if we add another molecule, notice I've highlighted this last molecule here in yellow because I want you to look at the delta negative and the delta positive. Now they are actually reversed of what should be, so this is a repulsive force, because it's just like when you try to stick the two ends of a bar magnet that are the same, i.e. the black ends or the red ends, so the two red ends together, that doesn't work. They are repulsive and they pull away. Or the two black ends, they're repulsive and they pull away. So this is a repulsive force with the same charge, so either delta negative, or delta positive, and this will force that last molecule that's highlighted in yellow to flip and reorient itself correctly, and like that's what I've done right here. And this will have now a dipole-dipole interaction that's correct. All right, so this is a generic example here of an intermolecular force of a dipole-dipole interaction. Now I'm going to show you a real-world example, and that's with carbon monoxide. So carbon monoxide, the delta negative is with the most electronegative element, and that would be the oxygen. It is more electronegative than the carbon, which has the delta positive end. Okay, and this will align itself with another carbon monoxide molecule. This is a dipole-dipole interaction. And subsequently, more and more carbon monoxide molecules will interact with each other in this same way. Okay. Consequences of a dipole-dipole interaction is observed with an increase in boiling points of similarly massed molecules. So I'm going to show you two different examples. One here is with nitrogen. Now nitrogen is a nonpolar molecule. It has a molar mass of about 28 grams per mole, and its boiling point is negative 196 degrees Celsius. In comparison of carbon monoxide, which has the same molar mass of 28 grams per mole, it is polar, and therefore there are intermolecular forces, okay? And since there are intermolecular forces, then the boiling point for carbon monoxide is higher than that of nitrogen, even though they have the same molar mass. If they have the same molar mass, then they should have the same boiling point. But because there are intermolecular forces, albeit very weak ones, the boiling point of carbon monoxide is higher. I'll give you another example, and that is with bromine, which has a molar mass of 160 grams per mole, and that is a nonpolar molecule, and its boiling point is 58 degrees Celsius. Whereas iodine and the chlorine combined together, it has a similar molar mass of 162, But that increased molar mass of 2 grams per mole does not account for its much, much higher boiling point of 97 degrees Celsius. What accounts for that is the molecule's polarity, and since it's polar, then it will have intermolecular forces with that ICL. Okay? That is another Crazy Hat video, and I'm feeling kind of like an animal today. Okay? So have a great day. Give me a thumbs up if you like that video. Subscribe to my YouTube channel, and I'm going to see you next time for more cool chemistry videos. Bye now.